In the last lecture, we are discussing the Bode plot representation of frequency response of linear time invariant system, which has transfer function of this form, or simply Bode plot of TS. In short, TS consists of this constant, and this can be integrator and the denominator, and the single pole, single zero, double pole, and double zero. Our assumption is the transfer function itself is given by this in this form in advance, or we factorized with some approximation, so we factorize in this form. Anyway, transfer function is shown in this form, and we covered each of these, Bode plot of this, each of these, okay? And there are two other terms we need to consider. That is this one, 1 divided by 1 minus S divided by omega P. This is RHP, pole. We covered this, and also later on, next, we'll deal with S divided by omega G, which is RHP 0, okay? So this is the basic structure, and the rule of the sketching steps of Bode plot is proposed by Hendrik Bode long time ago. He has a famous book. I wrote down his book name. The famous book is Network Analysis and Feedback Amplifier Design. It was published 1945, so it has more than 60 years. In that book, he mentioned that he proposed the way of sketching this using only linear line segment. So everything is just line segment, and the idea is we learn how to represent each of these multiplication factor with just line segment, or connection of the 2 or 3 line segment, and how to combining them together to get the entire Bode plot of TS. Okay, that is the approach he proposed. So basically, that is the asymptotic plot and asymptotic analysis. And the rule here is we only have these components. So if you have this kind of structure, there are 4 reactive components. So that is the first order system. So there is no rule for the first order system. Then we split them into 2 quadratic second order terms. For example, there's L, C, C. This is a 2-stage low-pass filter. If you select the component, one is much larger than the other, same is true here, then you combine these together, and you combine these smaller ones, then you have 2 separate quadratic functions, second order functions like this. So this is one factor, and this is another factor. So maybe S squared is appearing here, another S squared is appearing here. So with some assumption, so there is some assumption to factorize the first order equation into 2 separate second order equations. That assumption is usually automatically met if you select one component is much larger than the other one, and vice versa. Okay, that is the equivalent to saying have the separate time constant or separate corner frequency. If everything appears in the neighborhood, they are all mixed up. So this might be very difficult or impossible. So if you need to design something, use different values, okay, to obtain the composite effect of first order filter. So for this case, there is one double pole appears here, and another double pole appears here. So that is just the connection of the 2 double poles, and this double pole frequency is determined by larger guys here, and this high frequency double pole is determined by smaller guys. Okay, that is the Beijing rule. Okay, so that is the rule proposed by this Hendrik Bode in his book. Okay, I read his book. I read maybe 2 days ago, and very simple statement. He said that my purpose is to draw the frequency response plot of any transfer function using just linear line segment, okay, which is the asymptotic approach or asymptotic plot. Okay. So we went through all of this, and last time finally we analyzed this one. So let me start with that one. So I move that page. That page is here. Okay. So this is RHP pole. This pole it has minus sign in front of this. So pole is appearing here. Okay. So you don't see this much in practice because this system is originally unstable. Pole in this region, this is right hand plane of S-plane, it produces this kind of mode which is exponentially growing with fixed input or zero input or the impulse input. That is the definition of unstable response. Okay. If this pole is located in the left plane of S-plane, it has this exponentially decaying term. If some noise is triggering the system, that noise spike will generate this term, and this term soon dies out. The system is stable. Okay. In terms of this magnitude equation and the phase equation, magnitude equation remain the same because we are scaling this minus sign. So this is the same as regular pole, but this phase, this minus sign is coming in front, so it cancels with this minus, so this becomes positive. So in terms of magnitude, it is still pole, but in terms of this phase, it is 0. Okay? This was the RHP pole, and let's discuss about this. This is RHP 0. Okay? So RHP 0 has negative sign here. So you move this negative sign down here. So then this 0 is located in the right-hand side of S-plane. So this is 0. This is RHP 0. This is okay. This had some problem, but system is still stable. What determines the stability of any system is the pole, not 0. So 0 is totally independent of the stability of the system. So you can have this RHP 0 and you can have RHP 0. Okay? And we'll be seeing this very often. So all the PWM converters except Buck and Buck-derived isolated converters, all of others has this RHP 0 in duty ratio to output transfer function. That is the one big problem of PWM converters. As you will see, this RHP 0 is very bad in many sense, and we'll discuss that them one by one. All right. So let's take a look at this. This is the magnitude equation. So you are scaling this minus sign, so there is no effect. Okay. This magnitude is increasing like this. This is regular 0. Okay. But phase has a negative sign here. This guy is coming in front. So you have this minus sign. So that means in terms of this magnitude, this is still 0. And when you take a look at the phase, this is characteristic of single pole. Okay. So RHP 0 is regular 0. If you are only concerning with magnitude, but if you take a look at the phase, there is the pole, not 0 anymore. Okay. That causes a lot of problem. One unique problem of this is if a system has this kind of term, this RHP 0 term, that initial response of something. So this is T, and you have some electric car, and electric car has this RHP 0. Then this happens. You want to increase your speed in forward direction like this. This is the input. then response, angular velocity of that vehicle or that tire is initially it goes backward. Initially it goes this reverse direction and it will go like this. This can be very large. Okay, this is very bad. Okay, you want to go forward, but your vehicle is moving backward. Initially, that causes some problem. If you are taking the lifter, elevator, with this feature, and your elevator, when you get in elevator, it goes up before going down. Okay, you will be very uncomfortable with that kind of problem. This is the inherent problem of this system with RHP 0. Another problem is this is 0, usually 0, boost phase by 90 degrees. That helps the control design. Phase boost is something good. Phase delay is something bad. That hurts you. That does harm to you. Okay? So this is a poor, this is a 0, but in terms of phase becomes negative. It causes 90 degree phase delay that complicate the compensation design and the evaluation of closed performance. So with systems, with converters, this RHP 0 is very hard to control and very difficult to obtain a satisfactory performance. So we need special treatment for that. So you should pay very careful consideration on that. Okay. So second one is bad or unfavorable, undesirable phase characteristics. Phase characteristic or phase delay. So in terms of magnitude, this is regular 0. But in terms of phase, this behaves as poor. Okay, that causes problem. So this will come to later again. So I'll elaborate some details about this problem with this. Okay, it occurs several times. And next is how to draw the Bode plot of composite transfer function. So we covered each item by item, multiplication factor by multiplication factor. But usually transfer function is combination with this product of them. Okay. Then you take this one. So we take 20 log magnitude of this. The Bode proposed using this scale. The apparent advantage of this is multiplication becomes addition in log scale. So we have addition of this. Okay. Maybe we plot this one using just linear line segment. This individually. Then we combine them together. By adding them together, we'll get the composite curve, magnitude curve of this transfer function. Okay. Phase is this multiplication of this. Phase is addition. So phase is addition. Also, this magnitude is addition because Bode selected this log scale here. This is one good idea. And another idea is he's using semi-log scale here. Okay? So let's consider this one by one. This is the asymptotic plot of this term. And this is asymptotic plot of this single pole at 100 radian per sec. So it follows 0 dB line and it decays with -1 slope. Okay? And this S is increasing with this with +1 slope. This is a notation you are using previously. -2 is -40 dB slope for decade, and -1 is half of that, and +1 is 20 dB increase per decade. Decade means 10 times increase in frequency, and this is what? 40 dB. 100 times increase in magnitude as frequency increase 10 times. Okay, so this is this first one, and this is the second one. You have another one here, and this one is pole is located at frequency. So up to this frequency, we have 0 dB line, and we have another line segment. Okay, so we have this, and rule is add them together. So this is when you are interested in low frequency. So when drawing this, you start from the low frequency. This is a 0 frequency, very low frequency, and this is the 100. This is 10 to 5. So start from the low frequency. So at low frequency, just consider this. This is the line segment. This is the differentiation, and the 0 dB crossover frequency is 0.1, because when this is 0.1, this magnitude becomes 0, then it's 0 dB. Okay, so this is the one, this one, right? And the slope is +1 at it crosses 0 dB at this frequency, 0.1 radian per sec. This first one, and this second one. And when you start the plotting the entire plot from this direction, from low frequency to higher frequency, at low frequency you have here. So this is 0. There is nothing to add. So 0, and up to this after this point, you have this term. So if there is a no, they are not there, then it will increase forever. But there is this pole here. So pole is lowering down this slope. So this increase with the +1 slope, this decrease with the -1 slope, then it becomes flat. Okay, so it goes forever on this horizontal line, but at this frequency there is one additional pole. So this pole is lowering down this by this slope, so it starts declining with minus slope at this point. Okay, so this is a plot. So overall plot is go to there and go to there, and this line segment. Okay, the composite line segment is a Bode plot, asymptotic plot, as originally Bode proposed. But if you have more accurate plot, just lower this by 3 dB at the corner. So this is called corner frequency, and smoothly connect them. Then this is your very accurate plot, frequency response of this transfer function, or the system of having this equation as its transfer function. Okay, understand it, right? Okay, how about phase? This is a phase, so you have J here. So phase start with 90 degree, and you know this. So at this pole, phase is declining by 90 degree, and the slope is here at this pole frequency. This phase is reduced by exactly 45 degree. So 90 degree minus 45 degree is 45 degree, and after, if the frequency is increased 10 times, then another 45 degree, then it becomes 0. Okay, so it starts from 0 at 90 degree and goes down to 0, and this horizontal line means phase is 0. This is a real number, so phase is 0. It stays 0, and at this point, no, before this point, actually pole is there, but the phase of this plot is affected at this frequency before tenth of this frequency. Okay, there is a characteristic of phase. So phase is affected here. The magnitude is affected at the pole frequency, but it decreases like this, and it goes to minus 90 degree eventually. So final phase is minus 90 degree. All right. So this is the general way of drawing the Bode plot. Okay, and it shows all the important features of this Bode plot. Okay. If you are interested in low frequency below this, just you take a look at this. Okay. If we are looking this transfer function at this frequency, that is the same as simple differentiation. If you take a look at the interest in this transfer function below this frequency, then you only take a look at these two terms, but if you are interested in the entire frequency range, then you need to take a look at all of these. All right? This is a very, very desirable one, but you have this equation, but at low frequency, you ignore this. Okay? Just take a look at this, then that is the whole information is contained here, because this higher frequency pole is only effective frequencies beyond these frequencies in terms of magnitude, somewhere frequency from this frequency in terms of phase, right? So that's one thing. So this naturally divide the response by the location of the corner frequencies and the ranges of your frequencies of interest, right? Another benefit of this plot is, if you take a look at this, at this point, it is slope is -1, then phase is -90 degree. Okay, you don't care this phase of before this frequency. If you at particular frequency, you take a look at slope of magnitude, then phase is 0, and this is +1, phase is 90 degree. Okay, so it carries the information about magnitude plot and phase plot at particular frequency simultaneously. Okay, there is another benefit of using this Bode plot format. So I think this is the most desirable form, because it just shows the overall behavior of this frequency response, and it shows the frequency below this region only, just considering this. Okay, it shows the frequency response below this frequency by just considering two terms. All right, something like that. Okay, there is one thing, and we'll be using this for the future. So I won't say -40 dB per decade. I'll say just -2 slope, -1 slope, +2 slope, something like that. And this shows, the equation itself shows many things, because this order of numerator is 1, there's a 1s, and there are 2s, okay? S they cancel, so 1s is remaining, then s is integration, final slope of this magnitude curve should be -1, okay? It cannot be -2 or 0, all right? Final phase of this plot is, it has 90 degree, and -90 degree, -90 degree. So final phase is -90 degree. So it shows from the equation the final slope and the final phase. Okay. As I said previously, the impact of this pole in magnitude, it occurs at the pole frequency, but phase is occurring 1/10 of pole frequency. Okay. You will see effect of this at this frequency, 1/10 of pole frequency. So this is very easy to see, but until you reach this point, you don't tell whether there is a pole or not. Okay? But from the phase information, you can predict the pole is coming ahead, something like that. Okay? So there are many information contained in this plot. Okay? But you don't have to do this every time. Whenever you plot this, Bode plot of this, you don't have to do this, just doing once. And understanding the background behind this, and understanding the benefit of this plot, just once is enough. Okay? So you understand this once, then you never draw this again. All right? There's the waste of time. If you have everything in mind, there is an easier way to sketch the asymptotic plot of frequency response, namely the Bode plot. So suppose this is the transfer function, another transfer function. So just plot Bode plot of this, okay? In exact sense, just plot Bode plot representation of frequency response of linear time invariant system, which has Ts as its transfer function. Okay, That is the full statement. In short, we just say it, draw the Bode plot of TS. Okay. So for this, you should convert this. I said this is frequency response form. So you put out everything here. So put out this, and do the some multiplication and the division. So you have this, and this term has 1 plus S divided something. This is frequency response form. So you must change any transfer function in this form. Okay. So this is the frequency response form or standard form. Okay. So this is the plot. So initially it has, this is the integration. So it starts with +1 slope, and this +1 curve is looking at this frequency. Okay? Because when frequency is 250, frequency is 250, somewhere here, then initially it's looking like this. Okay? Then at this frequency, this becomes 1, which is 0 dB. So start with this, and if there is no other terms, then it will go this forever, but there is a 0. Okay? 0 comes first, so 0 increase phase, magnitude slope by 1. What I mean by 1 is, it is this +1 slope, then the slope is +2, which is 40 dB increase per decade. So this +2 slope, it will go forever like this, but you have a pole at this frequency. Pole is 225, so at this frequency, this slope is decreased by 1, so it becomes +1. And at this frequency, you have another pole. Then it becomes 0, okay? Go straight line, all right? So this is the magnitude curve. So if you want to obtain the exact prediction, just smoothly connect that and leaving 3 dB distance. This point, but this is not necessary. Okay, just plotting with asymptote is more than enough. Okay, and another one is this phase curve. This S is J omega, so there is a 90-degree phase, right? And okay, let me say this first. Take a look at this. Then at high frequencies, okay, so this is the 2, S is 2, S is 2. That means it settles in this horizontal line because order of denominator and order of denominator is the same. That final line should be gotta be this horizontal line, and that value will be 0 dB exactly. It will be the horizontal line, and that line will locate and reside on this 0 dB axis. Why is that? Because at high frequency, this is very large. This guy, they are gone, and this is S squared, so that is 1. Okay, so it settles in 0 horizontal line, and that line actually becomes 0 dB for this case, because this is the coefficient of the highest term. Highest order term is 1, so it settles in 0 dB horizontal line. So this is the exact one, right? How about the phase? Phase start from this S is 90 degree, and the final phase is there are 2 S's, so 180 degree. There are 2 S's in the numerator, minus 180 degree, so final phase should be 0. Okay? In between, you don't have to know. Okay? It goes up and goes down, so you are not interested in this. You just draw this arbitrarily. Just knowing this and this is more than enough. Okay? Don't pay attention on this. That is useless. Okay? So this is the way of sketching this Bode plot, right? Okay, I think you have enough knowledge to sketch any transfer function given by in this factorized form. So let's have a very short break. And in next session, I'll provide some examples, simple examples, yet very informative examples to sketch the Bode plot of transfer functions. Okay.